Okay, so I've started recording, Yassi, if you want to say a few words about the organization.
Sure. Thank you so much, Susan. Good morning, good afternoon, good evening, everyone, depending where you are. I'm Yassi Moghadam. I'm the Executive Director of International Society of Service Innovation Professionals, where these series we sponsor. We have collaborated with IBM to sponsor these series, and basically cognitive computing is a major enabler of services. That's why our organization finds these series and cognitive computing and AI a very important component of innovation. So thanks everyone for being here. And Susan, I'll turn it over to you.
Thank you very much, Yassi. And now I'm going to hand over to our two speakers who are going to introduce themselves. Please go ahead.
Yeah, hi everyone. So this is Patrick Stuedi here. I'm a researcher at the at IBM Research at the Zurich Research Lab, part of a team where we're doing lots of research on how to integrate modern hardware into the data processing stack. That is fancy networking hardware or new storage technologies. So how you want to best integrate these technologies into data processing systems, into cluster processing systems. So that's roughly the theme of the working group I'm in, and I'm going to present together with Jonas our project called Crail, which is a research project we started 5 years ago, that has recently gained Apache incubator status. So that's enough from my side for the introduction, and I hand over to Jonas for the intro. Jonas, you want to say a few words about yourself?
We don't hear you, Jonas. Maybe we need to unmute you, or? Ooh, we don't hear Jonas. And he's not, let me just check. Ooh, he's not, okay. Not sure what's happened to him, but maybe he's sharing his screen. So we're all on screen on slide 1. So if you want to go ahead, Patrick.
Yeah, I can continue, and hopefully by slide 17, when Jonas is going to take over, he's
and I'll work on trying to unmute him.
Yeah. Okay. So as I said, I'm going to talk about a project that we have started at IBM Research 5 years ago, which is called Crail. So Crail, essentially, in a nutshell, is a very fast distributed data store that allows you to store ephemeral data in there. That is data that has a very short lifetime. You encounter such data in modern data processing platforms like Spark or Hadoop or TensorFlow. An example of such ephemeral data is, for instance, shuffle data that is generated as part of a job. Another example of ephemeral data is temporary data that you basically share among different phases, across different phases in a complex data processing job pipeline. So that's where Crail comes in. Crail is going to be the data store that helps you to store that type of data efficiently in a very fast manner. So this talk I'm going to describe how Crail works and what were the main kind of motivation. What was the main motivation behind Crail? So this is taking me on page 2 of this deck, which is where I want to start. I want to give a brief kind of like intuition. What were the 2 main reasons why we started Crail? And basically, the first motivation, which you see on page 2, is that over the last couple of years, network and storage performance has substantially improved, right? So whereas like 4 or 5 years ago in a data center, you would run a 1 gigabit network fabric. Today, most data centers run 10 gigabit Ethernet. On-premise clusters, you can easily get for an affordable price 40 gigabit Ethernet, 100 gigabit Ethernet is out, 200 gigabit Ethernet is going to come. So that's a substantial improvement in terms of bandwidth. At the same time, we have also seen much lower latencies in these clusters with better switching, better end-host data processing. So round-trip latencies in a cluster have gone down from several, like tens of microseconds all the way to maybe 5-10 microseconds. So that's the network side. On the storage side, similar things have happened, right? We have seen Flash being deployed in a data center, giving you tens of gigabytes per second throughput at latencies of 100 microseconds or lower. And in the future, we will see non-volatile memories, phase change memory, 3D X-point, these type of technologies that give you even lower latencies. So that's one trend that we have seen. I/O performance has substantially improved over the last year. And on page 3, the second motivation is that we really see a lot of diversity in terms of hardware, particularly in terms of networking and storage hardware. So we have different end-host architectures like RDMA. We have different storage technologies. I already touched on 3D X-point, non-volatile memory, Express, a new way to access these technologies over PCI. We have a future where non-volatile memories are potentially directly attached on the memory bus. All these kind of things are happening. And at the same time, on the software side, we have new network and storage stacks that have been deployed. We have RDMA as a network stack. We have DPDK and SBDK as other like high-performance network and storage stacks that are available in the open space. So these two trends, the better performance and the higher diversity of network and storage hardware, have basically motivated the project we call Crail. And the initial idea we had was, given that we have all that fancy hardware, can we just integrate that hardware in a cluster and run a standard, let's say, software on top of it and improve analytics or data processing workloads with this? And this is unfortunately not that easy. As you can see on page 4, this is an example of a Spark TeraSort workload that we deployed on a 100 gigabit Ethernet network. And you can see, I mean, TeraSort essentially is a highly I/O intensive benchmark. It's or workload if you want. I mean, most of the all of the data that is actually read from the input source has to be shuffled across a network fabric and sorted out in the end. So this is highly network intensive. Nevertheless, on a 100 gigabit cluster, the network throughput, the peak network throughput of this workload never goes beyond 5 to 10 gigabits per second, right? And this is on a cluster that has actually 100 gigabits per second in terms of raw hardware firepower. So this was a big disappointment. So we were wondering what's going on in this scenario. And page 5 gives you a little bit of an intuition what is happening here. I mean, if you run traditional applications or frameworks like Spark or Hadoop on top of such hardware, you are essentially exercising pretty long software stack. So the application is typically running in a Java virtual machine. It has to get data copied out of that Java virtual machine into the operating system where data is buffered in socket buffers, is processed by the TCP/IP stack, is copied over to these buffers, and then DMA'd packet by packet basis onto the network interface. And that long code path is basically CPU intensive. You end up processing that stack on the CPU and spending a lot of time doing that processing, which prevents you from leveraging the fast hardware you have underneath, right? So that was one key observation we observed. So that brings me on to page 6, which was really where we started. We were like wondering, how can we leverage the speed of the fast hardware so that we can actually see a TeraSort workload performing at the speed of like 70, 80 gigabits per second rather than just 10 gigabits per second. And so we developed Crail. This is on page 7 now. And Crail, as I said before, is a really fast distributed data store that is designed to store ephemeral data like shuffle data, broadcast data in Spark, temporary data, etc., and is also designed to explicitly take advantage of new I/O hardware. So it's designed for RDMA hardware, NVMe storage hardware, etc., etc. It's really trying to make use of that type of hardware and the capabilities that hardware has, as opposed to using standard disks and slow 1 gigabit networks. And Apache Crail started as a research project at IBM Research, and we have just recently made the entire project open source and also attached it to the Apache incubator community in a way. So Apache Crail is now an official incubator project since January this year.
Oh, can I take a quick interrupt? There's a question in the chat asking you why is it called Crail and where the name comes from. And the second reason for the interrupt is, Jonas, you're no longer connected to audio. I can see that. So I've written in the chat.
Can you hear me?
Oh yes, we can hear you now.
Yeah. So I figured out how to unmute on the phone because I'm connected on the phone as well as on the computer.
Oh, okay, got it. Okay, good. Excellent.
Okay, welcome back.
Welcome.
Yeah, the first question is about the name, if I understand this properly. The name Crail is actually coming from the original implementation of Crail was basically an in-memory data store for RDMA networks, and Crail stands for cluster RDMA something, actually. So I don't remember the actual abbreviation properly, but it was derived from the fact that it's an in-memory data store designed for RDMA. By now, that has changed, and Crail is actually a multi-tier data store incorporating flash, non-volatile memory, and NVMe over fabrics, etc., etc. So the Crail is sort of an old thing where, reflecting the times where it was entirely an in-memory data store. So let me start with continue with slide 8. I mentioned that Crail is a fast data store for ephemeral data. So let's now look a little bit about what is so special about Crail, why Crail is actually allowing the hardware performance to trickle up in the stack, and what are the main key design decisions we made in Crail. So this is a little bit of technical part of the stack. So I'm on page 8 now. What you see here is the basic architecture of Crail. Crail, that slide doesn't show any surprisingly new architectural details. I mean, any sort of distributed storage system would have an architecture like this. So you have a name node which manages the metadata of the system, and then you have multiple data nodes. They are sort of offering the storage backend. This is where the actual data is stored. And the name node just keeps track of which object is stored at which data nodes. Objects can be large. They can consist of blocks. They typically consist of blocks, and these blocks are sharded over the data nodes, and the metadata name node keeps track of which objects has which blocks and where these blocks are, right? And the client, when he wants to read or write an object, he just contacts the name node to find out where the particular object is stored, and then is contacting that data node to read or write the object. So that architecture is very similar to what you see in an HDFS system. So now the question is, why is Crail so much faster or than an HDFS system or another storage system that is having similar properties? And there are multiple design decisions we made in Crail to make it really fast. So I'm jumping now to page 10. So the design principle number one is that Crail is inclusively based on user-level networking and user-level storage. So you can see the difference between user-level storage and traditional kernel-based storage on this slide. As I pointed out already on the first or second slide, traditional systems use kernel-based approach. That means the I/O requests are passed to the kernel. The kernel is taking the data, is copying through various layers, is instructing the hardware on a per block or per packet base to transmit that data. That's the same for networking and hardware. Both these stacks exercise a similar stack in the kernel. If you look at the user level approach on the right side, then what these approaches do is they essentially map the network or the storage hardware into user space and allow applications to directly access the hardware from user space. That's of course much faster because you don't have to go through many layers as before. You can avoid several data copies, and also you need much less CPU cycles to exercise in a user level approach. So Crail is entirely based on user level technologies, both for networking as well as storage. You can see we're using RDMA and DPDK, for instance, to exercise network operations, and we use NVMe over Fabric to exercise remote flash access. That's a new technology that is allowing you to access flash over an RDMA type of network. So I'm on page 11. I am actually fast forwarding here to page 12 to simplify a little bit. So if you take this idea of user level access and you extend it to actually the Java runtime, you can actually create a stack that maps your hardware into the Java virtual machine and access it directly from, let's say, your Spark framework. That dramatically cuts away layers in the stack, makes things faster, and that's what how Crail gets you the extra performance. We are cutting out several layers of I/O software by exercising user-level network and storage stacks. That's design principle one. So I move to page 14. So just a fast network and storage stack alone is not sufficient. It turns out that many data processing systems, once they have read the data from the network, that data needs to be serialized, and objects have to be generated out of that data, etc., etc. And there are memory buffers involved in the data processing framework, like Spark, etc. They have an entire subsystem around the network stack where the buffers are filled from the network, serialized, etc. So what we figured out is that aside from having fast I/O operations, we also have to be very careful in how we are handling the data that comes from network and storage. We have to be very careful in terms of how the buffering is done. We have to make sure buffers are constantly being reused. We have to make sure buffers reside outside the end, so we have a minimal amount of data copies, and we have to be very smart in how we deserialize and serialize objects. So we ended up even writing our own serializers and deserializers that fit with the Crail data store to get the best performance. That's design principle 2. Now I move to page 17. Page 17 is basically tackling the problem of diversity. I previously mentioned in the beginning that we have two trends. Crail is built on two trends. One is I/O hardware has got substantially faster. That's trend 1. And trend 2 is we have more diversity in network and storage hardware. And the design principle 3 in Crail is trying to incorporate that diverse hardware in a very applicable manner. So what we have is we have the core Crail store, which is handling the I/O operations, and underneath, as you can see in the more dark blue boxes, those are the backends, the different backends we have for different storage technologies. Currently, we have a backend for DRAM that operates over RDMA. We have a backend for flash that operates over NVMe or Fabric. We have a backend for flash that operates over iSCSI. And we also, not shown by the figure here, we have a backend that uses DPDK and SPDK to access remote flash. And Crail is made in a way that you can integrate new hardware technologies very easily by writing a new backend. So Crail is designed to be modular so that it can embrace future hardware technologies very easily. And one hardware technology that we have recently added, which is very interesting, is the NVMe over Fabric backend, which is where Jonas comes in, and he's going to talk about that.
Yeah, thanks, Patrick. Quick introduction from my side, since the microphone was not working before. I'm also working at IBM Research in Zurich, and I'm a software engineer here, and basically I'm working on everything related to state-of-the-art and next-generation storage and network technologies. And I'm also working on the Crail project. So, as Patrick said, we recently added an NVMe over Fabric Storagetier, or short NVMf. And NVMe over Fabrics is a quite new standard, which allows you to access remote storage, much like iSCSI for SCSI. It basically encapsulates NVMe commands over RDMA messages. And at the moment, there's basically one known user-level implementation of this, which is called Storage Performance Developer Kit. It's developed by Intel. But unfortunately, it doesn't have any Java support. So the first NVMf storage implementation that we did for Crail started as an API wrapper around SPDK. But we figured out that this is actually not a good fit for Java in the way how the memory is handled in SPDK and things like that. So we came to the conclusion that we have to have our own natively written Java NVMe over Fabrics client. This is what we did. It's called JNVMF. And there's also a link down there where you can find it. It's all open source. And it's completely standard compliant, which means you can connect to any other target. So this is basically only implements the client side of the NVMe over Fabrics protocol. And you're going to see in the next slide how this is used. And in contrast to SPDK and the kernel, it supports also many advanced features like arbitration support and things like that that are not supported yet by these other clients. And how we integrate this in Crail is basically, you've seen this picture before, but now we basically have a data node which connects to a target to get metadata information about the target, meaning how big are the disks that are going to be donated, and passes all the information to the name node. And then the client can directly talk to the NVMe over Fabrics target, could be a kernel target, could be SPDK target, via the JNVMF library to access data on Flash. And just to give you an idea, if you use this new Optane drives from Intel 3D XPoint technology, which has a raw latency of around 5 microseconds, you can do remote accesses from the client in maybe 12 microseconds, which is actually quite fast. Okay, then let's look at some performance evaluation. So the first thing is, let's look at a throughput of this NVMe over Fabric storage tier. And what you see is on the y-axis is the throughput in gigabytes per second. And basically 12 gigabyte is roughly the network limit. It's 100 gigabit Ethernet. And we have on the x-axis different kinds of message sizes. So from 128 bytes to 512 kilobytes. And what you see here is, if you look at the red line, which is called NVMe direct, which means there's no buffering involved. You directly put it on the wire and you pipeline it, and you see how fast you can get. And what you see is around 128 kilobytes you need to reach line speed from a client accessing this remote storage. Now, if you're a bit smarter, you do some buffering, some clever I/O scheduling, you can actually get to roughly the same performance that you get with a DRAM tier, given your access pattern is mostly sequential, at least for a certain size. But you see here, especially for most of the Spark applications, this is true. So that means we can basically push almost the same performance as we can with a DRAM tier by reducing the cost significantly, because flash is much cheaper than DRAM, obviously. Then let's look at the next workload we run. This is Spark. TeraSort application is a simple application, just takes data, sorts it, spits it out, sorted. And in the top, you see Crail, in the bottom is vanilla. And again, the y-axis is this time throughput in gigabit. So this is again a 100 gigabit network. And this is from one client machine. This particular benchmark was run on 128 machines. And the x-axis is the runtime. So you see, when you look at the runtime, that we are 6 times faster than vanilla. And you've seen this chart before. This is the 5 to 10 gigabits that Patrick showed. And we, with all these 3 design principles that we have in place, actually managed to push almost 80 gigabits per second peak throughput in the shuffle phases. And this was one of the reasons why we can reduce the runtime so much, plus the other changes that Patrick talked about that we did. So let's see. The next one is Sparkle with a SQL workload. And this is a well-known benchmark. It's called TPCDS. It's to be used to benchmark big SQL data stores. And what you see here is a CDF function of Spark vanilla versus Spark with Crail, running the whole TPCDS run, which consists out of 104 queries. And what it shows basically is that if you look at the chart on the y-axis, this is the number of queries, and basically the x-axis gives you how much faster this compared to Spark. So if you look at, for instance, number of queries, 60 number of queries are actually around 1.4 times faster running with Crail than with vanilla Spark. And we can speed up to 2.5 times. And there are very few queries which actually get slower, which we are still investigating why. And overall, if you look at the runtime on the right side, these are the 2 bars, you see that we are roughly 30% faster by running the same workload with Crail. Okay, and then comes the last thing, which I guess is most relevant for this call, since it's a cognitive call. This is running machine learning on Crail. And what you see here is we use a library to speed up the compute part. And on the y-axis, you have the execution time of a single task. And on the x-axis, you have 2 blocks, basically, which is one running the whole thing on the CPU, and the right side is running the thing on GPU. And then you have vanilla running Crail with an old stack, which we also support. That would be TCP, so user level IO. And then on the most right one is running Crail with user level IO, all the features we have plugged in. And basically, where we can only make a difference is in the red and in the green bars, because they are IO. And so this, in this case, would be the broadcast and the tree reduce. And you can see that for the CPU implementation of this logistic regression machine learning workload, we can speed up by a factor of 2 this workload. And for the GPU, we can speed it up by a factor of 2.5. So basically, the less compute part you have, the more opportunity for us to speed up the IO. If your application is not IO bound, obviously we cannot do much with plugging in Crail. But you can see here that there are lots of machine learning algorithms. If you plug in a GPU, you make the compute part small enough, you can actually see quite some gains by accelerating the IO. yeah, that's it from my side. Thanks. You can look at this address. You'll find all the information about Apache Crail, or just contact us on our mailing list. It's yeah. Thanks. Susan?
I was muted. Excuse me. So yes, thank you so much. There was a question in the chat. Marvelous achievement, very creative. Does the architecture open any new cybersecurity concerns?
I mean,
Patrick, you want to answer?
I'm not sure about that. I mean, we have. I mean, Crail is designed for basically the data center. It's meant to be operated by either the data center operator or by a single authority that manages the cluster. So this is not. I mean, a lot of these user level protocols, in particular RDMA or NVMF, they allow you to access remote resources with just very little information. So they are problematic from a security standpoint, but if you use them within a well-managed environment and that has other security barriers in place, I think it's not it shouldn't be a big risk to deploy these type of technologies.
Yeah, so you may want to. I don't know if there is any follow-up on that. You can follow up in the chat, or I'll just quickly ask the other question. Somebody Alex is saying, I watched your talk at Databricks. What is your take on using Crail in serverless to store state?
So yeah, so thanks for that question. So there is a recent talk on that we have linked also on the Crail website that talks about using Crail in a serverless environment. So that is pretty much the latest what we have in this regard. The serverless project is still going on, and we have probably a few more results coming up in a month or two.
Can you post the link to that in the chat, and can people on the call also thank our speakers if they enjoyed the session?
Sure, I will
do
post
that in the
link.
chat. Yeah, if you can post the link. Somebody was asking about the cute bird.
Yeah, the cute bird. It was. I think the penguin was occupied. So it is actually an oil. It's but if it's
is it an owl? Owl, OWL? Or?
Yeah, exactly.
Yeah. Okay. Yeah.
So.
Oh, I see the link now. Thank you.
It doesn't have a particular meaning, the oil, so it's just basically other birds were occupied.
Yes. Any more questions before we close? And any more thank you? I think we're done. Thank you so much for giving this talk. We'll upload the recording later today or tomorrow.
Yeah.
Great. Thank
you so much for having us.
Yeah. Thank you for the great presentation. Thank you. Bye-bye. Bye.
Bye-bye.
Bye.